Hello students, welcome to an amazing online study platform. As you all know, my name is Zoila today, and today we'll be taking it up from the part we stopped at the other class, which was named as part 1, but this one is part 2, which is chemical calculations. Alright, so before I go ahead, I would like to remind you of our normal routine that you should find a very quiet and conducive place to sit, and make sure you are not just sitting down. Be there with your notebook, your pen, and your textbook as well. So over to our objectives. These are the things we need to understand at the end of this very class. The first thing is we have to know how to... Okay, so like I said, first thing on our list under objective is to know how to calculate formulae. Okay, several formula which we need to know how to calculate. Then the second one is that we need to know how to calculate moles as per chemical equation, and you can calculate mole using chemical equation. Then same thing with calculating of formulae. So calculating formulae, we can find the moles of the element present in a compound if we know the formula of the compound. For instance, if we have 1 mole of a compound, then the formula shows the number of moles of each element in that compound. Okay, this is an example right here. For example, the formula for lead 2 bromide, which is PbPr subscript 2, that's lead 2 bromide. Okay, this means 1 mole of let's underline that, 1 mole of lead ion and 2 moles, okay, 2 moles of bromide ions. There's nothing like aeon. I severally hear some people call aeon. I don't think that's the correct pronunciation. So here we have 1 mole in this very compound right here, which is lead 2 bromide. Okay, we have 1 mole of lead ion and 2 moles of bromide ion. Okay, so but if we do not, say it's capitalized because there is a point I'm trying to bring out there. If we do not know the formula of a compound, we can find the masses of the elements present experimentally. Okay, and these masses can be used to work out the formula of the compound. So you'll see that next, which is there, finding formula. So I'm taking magnesium oxide as my case study this afternoon. So when magnesium ribbon is heated strongly, it burns very brightly. It has very bright color, so it burns very brightly to form the white powder called magnesium oxide. So here is the formula, this arrow, forward arrow. Okay, magnesium plus oxygen will produce or yields magnesium oxide. So this is how it's being done. Don't forget from our former slide, I said if we do not know the moles, so we have to find out the masses. Then from masses you can get masses of the constituent element. Then we can as well get out our formula from there. So this how it's been set up. Apparatus used to determine magnesium oxide formula. So here you have the crucible, is all named. This is the lead, and this is the magnesium ribbon inside there, and you have your Bunsen burner as it being attached to the system. So let's look at it. How can you get your masses? You know, initially, before you start your experiments, the crucible is kind of cup-like material, which you saw earlier. So you can weigh that in the lab. So for instance, I weighed my own crucible to be 14.63 grams. Okay. The mass of crucible and magnesium, don't forget we are using magnesium ribbon. Okay, when you weigh that ribbon and you add it to the one you weigh there, it will give you 14.87. so definitely you can get the mass of magnesium ribbon out from this. If you deduct mass of crucible from mass of crucible and magnesium, it will definitely give you the mass of magnesium used, which is this one which I put here. So that's 0.24. Definitely, if you had 0.24 to this, it will definitely give you what? 14.87 grams. So another thing is that mass of crucible and mass of magnesium oxide. You know, after burning the magnesium ribbon, your final product will be magnesium oxide, the white powder magnesium oxide. So you can always weigh this in the lab. You weigh this and plus this one you've known earlier. So both of them will give you this. So how can you now get the weight of this one? Just to remove crucible from this one. So this is my answer here, which is 0.16 grams. That's mass of oxygen which has reacted with magnesium. You know, it's not enough for you to write magnesium oxide, since we knew the mass of magnesium before. So you can always remove, if you want to know the mass of oxygen, you can always remove magnesium from magnesium oxide that you got. So that one will give you the mass of oxygen. I guess someone is getting what I'm trying to do here. So from this data, we can calculate the number of moles of each of the reacting elements. For instance, A subscript R, from your former knowledge of the part 1 class, this very thing means relative atomic mass. Okay, relative atomic mass. That's the mass of each element as given in the periodic table. So for oxygen you have 16, for magnesium you have 24. Yeah, masses reacting, you know, from our former thing that we got, you see magnesium is 0.24 while oxygen is 0.16. That's what I wrote here. So you have to do it like a table. When you are calculating that, you put magnesium here, you put oxygen here. So masses reacting in grams, that's G. G stands for grams. Okay, so for magnesium you have 0.24 grams, while for oxygen you have 0.16 grams. So how can you get your number of moles from that? Don't forget, number of moles equals to what? Equals to mass of the elements divided by what? AR. AR is a relative atomic what? Mass, or you can call it mass of 1 mole of that element. So mass of 1 mole of magnesium is 24. So divide that mass of element divided by mass of 1 mole of magnesium, which is 24 given here. So divided by that, you have your 0.1. Then 0.6, which is what was the experimental mass you got from your experiment for oxygen. Then you divide it by mass of 1 mole of oxygen, which is 16, sorry. So when you divide that by 16, you get 0.012. So the next step after these two steps is that you divide through by the smallest value. As you can see here, both of them are equivalent to each other. So 0.01, 0.01. So you are free to divide through by any of them. So that one will give you what? 1. This one will give you 1. So formula for this compound that you didn't know initially will now bounce down to, that means you have 1 what mole of magnesium and 1 mole of what oxygen. So you can now write it this way. This is your formula. Okay, so moving to the next slide now. This formula is the empirical formula of the compound. How can you define empirical formula? When you say empirical formula, it shows the simplest ratio, okay, ratio of the atom present. For instance, in magnesium, ratio of magnesium to oxygen is ratio 1:1. Okay, am I clear? So you have 1:1. So moving to the next, unknown compound. You know, we just deal with formula now. When you're talking of unknown compound, how can you know the compound? Okay, in another experiment, an unknown organic compound was found to contain 0.12 grams of carbon and 0.02 grams of hydrogen. Calculate the empirical formula for the compound. Don't forget, this relative atomic mass of hydrogen is 1 and relative atomic mass of carbon is 12. So when you want to do this, to find this compound, you have to follow that same procedure. Mass in gram, you have been given a mass in grams of carbon 0.12, the mass in grams of hydrogen 0.02. So when you divide to get the number of moles, don't forget at any point in time, moles equals to, which is acronym N, equals to what? Okay, equals to mass of carbon. For instance, we are talking of carbon, divided by what? That's AR, that's relative atomic mass of carbon. Your carbon should be capital C. Okay, so when you do that, what do you have there? We have 0.1 for carbon. Then for oxygen, you can replace this C with O for oxygen. So for oxygen, we have what? Sorry, for hydrogen, we have 0.02 divided by 1, which gives you 0.02. So the next step is that you divide through by the smallest value. What's the smallest value between this and this? Definitely is 0.01. So divide through by 0.01. This gives you what? 1. This will give you what? 2. So that means the compound, the empirical formula, that's the name, empirical formula, because it's showing the ratio of the constituent elements. Okay, so for carbon is 1 and for hydrogen is 2. That's why you have this formula right here. So from our knowledge of bonding, we know that a molecule of this formula cannot exist, of course, because for all carbon, carbon at any point in time must be bonded to 4 atoms. So that means you can't have just 2H. Okay, so there's still some gap missing. So for you to get the actual what? The actual formula, we have to do some things there. Okay, need to clean up that. So for you to get the actual formula, which is not empirical formula, you have to do some little calculation also. So from our knowledge of bonding, we know that molecule of this formula cannot exist. However, molecule with the following formulae do exist, like CH4, which is methane. This one is ethane. We have like that. It's C3H8, we have C5H10 and all that. They are numerous. Okay, so CH2 as our unknown now. To find out which of these formulae is actually formula for the unknown organic compound, we need to know the mass of 1 mole of the compound. So don't forget the way we calculated in the last class. When you want to get the mass of 1 mole of a compound, That's the molar mass in short form. So for you to get the molar mass, this is the completion of the question. Using a mass spectrometer, that's MR, which is known as a relative molecular mass of this compound, was found to be 56. So we need to find out number of empirical formula units present. So how can you do that? There's the formula you're going to use. So it will be number of empirical formula units present equals to what? Relative, you can say relative formula mass of the compound or relative molecular mass of the compound. Same thing, same MR. Then divided by relative formula mass of the empirical unit. So you see it in a bit. This is MR equals to 56, which is given. MR of the empirical unit is calculating your what? You have to calculate the mass of 1 mole of CH2. C is 12, that's 1 times 2, then 2 times 1 will give you 14. So number of empirical formula present will now be what? Don't forget, that's relative formula mass of compound, which is given to be 56, divided by what? Relative molecular mass of, relative molecular mass of the empirical unit, which is 14. Okay, 56 divided by 14 will give you 4. Therefore, the actual formula for the unknown compound is 4 times, this 4. It's like writing your CHN, CH2 times N equals to your what? Relative molecular mass. Okay, so something like 14N equals to 56. Just like the normal one, conventional one you knew before, so it will be 56 divided by 14. Your N equals to what? 4. So this is what we got here. And that 4, you multiply it by CH2. So times 4 will give you what? That will be C4H8. What do you call the name? Can I hear you? What do you call the name? That's butene. That's butene. Is a double bond compound. So this is called butene. C4H8 is the molecular formula for the substance, and it shows the actual number of the atom of each of the elements present in 1 mole of this substance. So this is how it goes. So I want you to try this now. I want you to try this. Try this for me. So calculate the empirical formula of an organic compound containing 92.3% carbon and 7.7% hydrogen by mass. So you are given the relative formula mass of organic compound to be 78. What is the what? Molecular formula. Relative formula mass is same thing as relative molecular mass. So you have to now get your relative, you have to get your molecular formula. You have been given your relative atomic number of H and C. Don't forget, this might look strange to you. This is in percentage, so it's quite simple. It's same procedure. You just divide by what? Get your number of mole by dividing by what you have been given already. So moles and chemical equation. When we write a balanced equation, chemical equation, we are indicating the number of moles of reactants and products involved in the chemical reaction. Consider the reaction between magnesium and oxygen, just like you have it here, which will give you magnesium oxide. So using the idea of mole and masses, we can use the information to calculate the quantity of different chemicals involved here. So for magnesium being solid, we have what? 2 moles. From balance, that's why I said you must always balance your equation. Like me now, I guess there's some mistake here. So there's supposed to be 2 here. So when you have two atoms of magnesium and you have two atoms of oxygen, will give you 2 atoms or 2 moles of magnesium oxide, which is what we have. That's why you can have 2 moles there. Okay, so 2 times 24 is 48 grams there. 1 times 16 times 2, you know, this stands for the subscript, so it's 2. So definitely same thing goes there. 2 times 24 times plus 16. This one will give you, or you have to do the bracket first. 40 times 2 will give you 80. So do you notice that the total mass of reactant is equal to total mass of products? If you add 48 plus 32, will give you 80. And you have 80 on the right hand side. That's how to double check if your chemical equation is balanced truly. So this is true for chemical reaction, and it is known as law of conservation of mass. Okay, chemists can use this idea to calculate masses of products formed and reactant used in the chemical processes before they are carried out. So we do example, you know, the initial one was calculating what's empirical formula and knowing the molecular formula. But here we are going to do something different. So lime, for instance, which we all know as quicklime, which is CaO, that's calcium oxide, is used in the manufacture of mortar. It is manufactured in large quantity by heating what? Limestone, which is calcium carbonate. Okay, so don't forget this sign stands for addition of heat. Okay, so when you add it to the system of limestone, it will dissociate to give you what? Calcium oxide and CO2. So you have to look at the equation. Is it balanced? Yes, balanced. So 1 mole of this gives 1 mole of this plus 1 mole of this. So how can you calculate this? Calcium is 40, carbon is 12, then you have 3 atoms of oxygen, which you have to do 48 plus 52, that's 100. Then this gives you 56 and 44. So calculate the amount of lime produced when 10 tons of limestone are heated. So on your metric conversion, you have 1 ton to be 1,000 kilograms, and 1 kilogram will give you 1,000 grams. So definitely your 1 ton will be equivalent to 1 million grams if you do your calculation well. But we will have a lot of decimal points, so I don't want to use that. So from this relationship between grams and ton, we can replace the masses in gram by masses in ton. So I just use it in such a way that in tons, wherever I have tons, I'll treat it as if I'm treating gram. Okay, just like we have 100 grams initially, so this 100 tons. You know, this acronym is a short form of tons. Okay, same thing as calcium oxide and carbon 4 oxide. So if you do that, when you have 100 limestone, we give you 56 tons of what? Quicklime, as well as 44 tons of what? Calcium 2 oxide. So when you now have 10 tons, what will happen? So putting 10 here now, don't forget how hard it to do it. Even if you don't want to divide through by 10, which is normal thing to do here, because to get 10 of calcium carbonate from 100, that means you have to divide by 10. If you don't want to do it that way in exam situation, you can always say, since 100 of carbon carbonate, we give you what? 56 of CaO. That means 1 ton of CaO, CaCO3 rather, will give you what? 56 divided by 100. Okay, then if you are now talking of 10 tons, 10 tons will give you what? is equivalent to 56 divided by 100 times 10. So if you do your calculation there, 1 here and here 10 divided by 56, 5.6. That's how I got it. So that means the equation now shows that 100 tons of limestone will produce 56 tons of lime. Therefore, 10 tons of limestone will produce 5.6 of lime. So example using gas. When you're talking of gases, many chemical processes involve gas. The volume of a gas is measured more easily than its mass. Okay, how can you do that? The example shows how chemists work out the volume of gaseous reactants and products needed using Avogadro's law and idea of moles. So you have to know that some rockets use hydrogen gas as fuel. That's one. Then when hydrogen bonds in air, in oxygen, it forms water. You know, it's combination of hydrogen and oxygen that will give us water. So it forms water vapor when it bonds in oxygen. So calculate the volume of A. The question is divided into two segments. A, you have to calculate the volume of oxygen molecule used or oxygen gas used, whichever one, and water in form of steam. That's why it's in gaseous state. So produce, if 960 dm cube, that's cubic decimeter of hydrogen gas were born in oxygen. So you have to write assume 1 mole of gas, of any gas, occupy a volume of 24 decimeter cube. Don't forget, that's the constant used as at room temperature and pressure, RTP, that we did in the last class. So when you have 2 moles of hydrogen, you know, after balancing it, this is what it gives you. On a normal day, you just write H2 plus O2 gives you H2O. But it's not balanced. Until when you balance it, you can proceed with your calculation. So when you balance the equation, it gives you 2 moles of hydrogen gas, 1 mole of oxygen gas, to give you what? 2 moles of water, steam. That's steam. It's in vapor. So 2 times, you know, we have been assumed 1 mole of gas occupy 24 decimeter cube. So you have to 2 times this, 1 times this thing. So you have your 48 dm cube for hydrogen. You have 24 dm cube for this and 48. So they now say, calculate the volume of oxygen gas and water of steam produced if 960 dm cube. You know, yeah, you got 48. What can you do to make it up to 960 of hydrogen gas? That means you multiply by 20. If you multiply by 20, it becomes 960. So you have to multiply all by 20. 20 times this will give you 480. 20 times this gives you 960. So definitely when you have 960 of hydrogen gas, definitely you have oxygen gas to be 480 dm cube, and you have steam to be this. These are what are being required whenever you do this. And you can as well, if you don't want to follow this formula, you can follow the formula I use, not quite long, like cross multiplication kind of formula. Since 48 dm cube gives, let's do that. Since 48 dm cube, okay, of H, we give you hydrogen gas, we give you what? 24 of oxygen. So definitely 1 dm cube will give you what? We give you 24 divided by 48. Then when you're now talking of 960 dm cube, we give you 24 divided by 48 times 960. Okay, so when you do that, you get what I just get here. You do that for hydrogen, that's for That's for oxygen. I did now. You're going to get 480. Then you follow the process and do it for steam. You get your 960. So example 1, using a solution. Chemists carry out reaction using solution. If you are using solution, for instance, you have this example here. Calculate the volume of 1 mole per dm cube. Okay? 1 mole per dm cube solution of hydrogen tetraisosulfate 6 required to react completely with 6 grams of magnesium. Okay, for instance, you are not given mole of magnesium, so you have to find the number of moles first. So how can you do that? Mass of magnesium divided by mass of 1 mole of magnesium will give you 0.25 moles. Don't forget this acronym, short form for moles. Okay, so then I'll ask you to calculate the volume. Don't forget our formula the other time. The volume, you know, concentration mole per dm cube in mole per dm cube equals to what? Moles of any solution divided by volume. So if you make volume the subject here, this is what you get, and you just slot in your parameters. Mole of H2SO4 is being given. Okay, we have, when you write the balance equation, this is what you have. You have 1 mole of magnesium reacting with 1 mole of this. At times it might not be 1, so you need to balance your equation. Make sure what is on the left hand side is same thing as right hand side. Okay, when you do that, this is what you have. Then you now use those parameters. Mole of hydrogen tetraisosulfate 6 will be 0.25, and concentration as given in the question is 1. So when you do that, you get 0.25 dm cube. Or if you are being required to do it in cm cube, you do that. But standard, most times you have to do it in dm cube. So using solution, this is another example. Following the steps, you have to calculate what? When sodium hydroxide solution used in the following neutralization, you have to calculate the concentration of sodium hydroxide, which is used in neutralizing HCl, hydrochloric acid. Okay, you have been given the volume of hydrochloric acid, you have been given the concentration. So you are being given the volume too for sodium hydroxide. You have to get your concentration. How can you get that? It's two-way thing. You can get it using your normal conventional molarity times volume. You know, molarity times volume is equals to number of moles, just from our normal formula. So molarity in mole per dm cube for for hydrochloric acid, you have to write the, don't forget, please always write the equation before you proceed, so you know the ratio of base to acid. Is very, very important. So here you have to calculate the number of moles of hydrochloric acid because you were not given. So you are given volume, you are given the molarity, so you can calculate the number of moles, which is 0.08. And when you do that, definitely, because you don't know the number of mole of sodium hydroxide, but because they are in ratio 1:1, definitely before they can neutralize each other, they must be in same ratio. So that's it there. Then when you now calculate the concentration of sodium hydroxide, you know the number of moles already, and you have been given the volume, definitely you can get your molarity, which is in mole per dm cube. And you can as well use this formula, which most of you are conversant with. Okay, so percentage yield. Many a times when you are having experiments, or if it's not experiments, okay, you are just doing theoretical work, chemical reaction really produce the predicted amount of products from the masses of reactants in the reaction. They are not 100% efficient. Why? An example of this reaction of the carbon with oxygen to produce carbon 4 oxide gas. This is the equation. So when you burn these 12 grams in 1 mole of oxygen, this is what you have. It will give you 1 mole of carbon 4 oxide. So definitely don't forget 12 gram will react with 16 grams of this, 16 times 2, and it will yield 44 grams of carbon dioxide. This only occur, however, if the reaction is 100% efficient. But when you didn't perform the experiment yourself, we are just to calculate. So for you to know the percentage yield of the reaction between this and this, you have to use this formula, which is percentage yield equals to actual yield divided by theoretical yield times 100. So this is an example for you to have a look. So the actual, you have been given, your actual number for carbon is 12 grams, isn't it? And you were told that it was born in excess oxygen and only 28 grams of carbon dioxide was produced. Okay, so the actual one will be over, you know, our actual for carbon dioxide is supposed to be 44 grams. Okay, and you have been given theoretical, your actual yield is the one given. So it's the reacting mass, actual mass or reacting mass, which is 28 grams. And your theoretical yield is the one you get from your balanced chemical equation, which is 44. So if we do actual over the theoretical times 100, you have 63.6%. So I want you to do this for me. It's same thing with what I've been doing since. So you have to calculate the concentration of potassium hydroxide solution using the following neutralization reaction. You have been given some value. Just get the one you don't have and use it to calculate the overall concentration of potassium hydroxide. Then the second one, number 2, is that you need to calculate the mass of copper required to produce 159 grams of copper 2 oxide when heated in SSA. That's using percentage yield. Okay, so stay happy and enjoy your day. Bye.